to interact with the file. And then we had the reading function so that we can read something from a file. And one of them you know already very well, hopefully at least, the fgetS function, where you read the string from a file. And you use this when the file was the standard input. And then there exist other functions like fread. We will see this also in a few minutes what this does, but this is now, it doesn't read the string, but it can read arbitrary data. So it depends on what you want to read. If you want to read integers or doubles, you can specify this here. And also there is the fgetC function. This is now the same as getChar for the input. Now, so fgetC reads a character, getChar reads a character from the input, fgetC reads it from a file. Then you also had functions to write to a file, which can, which would be, for instance, fprintf. I think I don't need to explain this function, you know this very well, but you just have the F for file in front and need to specify in which file you want to write. But this other functionalities are the same. Or putC for like writing a character to a file, or also the fwrite function, which is kind of similar to the fread function, where you do not necessarily deal with strings or characters or readable data, but it could also be like storing an integer into a file. And okay, why did this not work? Okay, ftell also a function. You can with ftell get the position where you're in the file. So think about being in a file as a cursor. So like if I switch to the code, if I move my cursor here, then I'm at this position in the file. And ftell would tell me, okay, I'm here in the file. And then I can also move the cursor around. So with the fseek function, I can pretty much set the cursor to any position that I like. And with the rewind function, I go back to the start. So basically, if I would say, if seek go 2 elements further, then I would jump to the next line and then jump over the next bracket.
Yeah. And VS Code has an implemented ftell down below here. Mm-hmm. It's kind of line 5, column 2, but it always says you where you currently are in your file. So it's a kind of ftell.
Yeah, you're right. Yeah. And yeah, I think that's like the basic functionalities. So let's see how we can create the file. So maybe move to the create file function here. Okay, first thing, to create a new file, we have to open it, but it doesn't exist. But this is not a problem, because if we open a file to write to it, then it will be created. So let's call fopen. Then I need to specify the file name. So I think I've chosen ISP file.txt. And this is a string, of course. And I need to specify the mode in which I want to open it. Now I want to create it and write something to it. So I'll choose the mode W. And maybe this is now a bit awkward in the first moment. This W is then passed as a string. So you need the double quotes and not the single quotes. Why is this?
Yeah, because otherwise it would be a variable. If you do not use... okay.
I mean, why don't we use the single quotes here?
Okay. Yeah, because you can have, for example, V+, W+, R+, and whatever. So there are different combinations that could be also a string. In this case, it's a string with 1 character.
So we need to use the double quotes here.
Yeah.
And what do we get? We said we get this file object, and this is... We don't get it like as a variable on the stack, but we also have a pointer to it. So this is, you can think about that the file is stored somewhere on the heap and you get a pointer to it.
Yeah. And this file is nothing special. It's basically, it's just a number, a reference to a specific file. Yeah.
Yeah, so it's just an indicator which file we mean, and some other informations like where we are in the file, for instance. So what do we need to do next? Has somebody an idea? If we have opened the file. Yeah?
Yeah. So was it successful? In this case, I think I can spot the file name in the current directory. It's here, yeah. So hopefully it will work. But if not, we have to check if the file exists, and if not, what do we do if the file does not exist?
Yeah, we print maybe some message, file cannot be created.
Yeah.
And we return because we cannot continue. So let's see whether this works, what we have coded so far. So let's compile create file.c, and I will remove here the ISP file for now. And I compile it and run it. Okay, now this file got created again, but it is empty. Even though we did not even close the file. Yeah, so it did this kind of, we were lucky that this worked, but this is really important. We also need to close the file at the end.
If we would not close it, we would get memory leaks again.
Yes, this is true. And maybe some content is not written to the file. So we always open it, check it, and close it. If we would specify some weird path like this, I think we should go into the error message. Yeah, because in this case, this would mean, okay, go to the directory A, but in this directory, in the KU10, I don't have a directory called A, so I cannot go to the directory A and create the file. So this will then fail, and that's why we catch this error here. Let's remove this again, so it works. And now we can write something to the file, and maybe write some message here. Hi ESP, maybe a \n also at the end. And now it is very easy because we can just use kind of printf, but instead we use now fprintf. We additionally specify the file that we write to, and everything else is as printf. So maybe we write %s and then the message. So this part is completely similar as printf. We just specify the file and write here the f in front.
And if you would write instead of file std out, it's completely the same as printf.
So we can also try this then if you like. So let's compile it first in this version. If I create now the file, the ISP file still exists. It also existed before, but now in this case we have hi ISP now contained. So I've written to this file. Maybe to demonstrate this one more time, I delete it again. It's now gone. I just need to run the code, and then it's again created and it contains the right thing. So whenever I call my program now and the file exists, it will delete the file automatically, and or differently spoken, it will overwrite the content. It will delete it, open a new file, then we can write something to it, and this will be stored here. So for instance, if I would do this twice, and okay, now I need to compile and run it, then the file contains 2 times the hi ISP. Okay, now we've seen this, the fprint function. Now we also saw the fwrite function before. So if we want to write the message using fwrite, what do we need to do? We need to specify first a pointer. This is the pointer to the buffer. Every string lives in an array, so we need to pointer to the buffer, to the array. This would be message.
Yeah, so the string we want to write to the file.
Then we need to specify the size, and the size refers now to the data type that we are writing. So a string is now consists of multiple characters. So we write here 1 or better size of char.
Yeah. So the size of one element in the array.
Genau. And then we specify again some size n. So this is then the count of elements that we want to write to. And this string has now, or I can do it differently. I just use the string length function of the message. So this is how many characters I want to write. I don't want to write a null byte into my file. Why? Because I don't need it there. I just want to have the string no null byte here, so we don't write the null byte. And then the file where I want to write to, so this is again the file.
Is the new line written to the file then?
Yes, because it's part of the string, and for this reason we will write up until the null, the \n, but not the null byte anymore.
Okay, so cool.
So let's get rid of this, just write it with fwrite to the file. We have now in the file, we have it twice as before, and now we just write it once, so it should then overwrite the file, and the high ISP is just contained once. And if we do this now, it's just contained once. Okay, so we have created now a file. This worked out very nice. Maybe let's jump now to reading this file that we have created. Okay, so we again open it. This works now the same way. Call it again a file. We open it. The name should be the same as before. It was ISP file.txt, and now we specify the reading mode. So again, same procedure with files as before. If the file is null, then we can print cannot open file and return with some error code, for instance. And I also immediately close the file at the end that I don't forget it. What is now contained in the file? So I could even move it to the right side so that you can see it. What is contained in the file? This is some obvious question maybe, yeah? High ISP, so 8 characters, if you count it, yeah? 8 characters, yeah? Has somebody another idea what is contained in the file? Mm-hmm. Yeah, so end of file is also kind of there, but it's not really stored in the file. Mm-hmm. Yes, also the line break is here, basically indicated that there is a new line, but these are like these.
The line break is basically the last character.
These are these 8 characters are highlighted. Okay, this is a tricky question.
Yeah, so what do you want us to know?
So this is a character, so like let me do this. Okay, so what I have marked now are 4 characters. Every character is stored in exactly 1 byte. So we have now, in the blue marked text, we have grouped 4 bytes. Why cannot these 4 bytes form an integer? So these are 4 bytes, they are consecutive in the memory, they are by chance exactly related to the letters H, I, then a space, and then a large I. Why is this not an integer? Because it's 4 bytes. So we can also interpret this as an integer, basically. And then here, this S, the P, the exclamation mark, and the new line are again 4 characters, so there are 4 bytes. Why is this not also an integer? And why is not then the whole string an array of 2 integers? And the answer is yes, it is also. This is also true. It depends on how you interpret the content of the file. So this could be 8 characters, so a string. It could be 2 integers. It could be a double of size 8. It could be the address of a variable because it's 8 bytes. A pointer also has 8 bytes. It just depends on how you interpret it. Okay, now after this discussion, now let's maybe stick with the character first. So we said very obviously it is a string of 8 characters. How can we read it? We would like to find out the size maybe first. Because I see here the file, okay, here we have high ISP, and I see there are 8 characters stored. But your program doesn't know at the moment. So we would like to find out the size of the file, and then we can create a properly sized buffer and store the content of the file into the buffer. How can we do this? Now we can use the function ftell for this.
So there is no file size or file length function, unfortunately. We have to calculate it on our own.
So the ftell function, we said it returns the position of the cursor. So if we call ftell with the file, then we get some position.
Yeah. And in the beginning, so when we open the file, the position is always on before the first character. So in this case, before the H.
Let's see to which value this then maps. Maybe this maps to some weird value, I don't know. And then we would like to go to the end of the file, also measure the other position. So fseek, we go in the file. Okay, this is now this offset variable. I will set this to 0 now, because I can here at the end specify where I want to set my cursor. So seek end. So I want to go to the end of the file. And here I could specify, I want to go to the end of the file, but -2, for instance. So 2 positions before the end of the file. But let's set it to 0 because I really want to go to the end of the file. And now I take size t end position maybe. Again, call ftell. And maybe now let's print the 2 positions. Since I used the size t, this is basically a larger integer as an unsigned long. That's why I wrote here unsigned long instead of %t. Initial position and end position. Okay, and let's see what this does. Read file.c. Okay, now if I read it, then the first output for the initial position is 0. So really the cursor starts at position 0, and this is the start of the file. And 8 is then the end of the file. So we could basically say, okay, end position, we directly rename this to file size, for instance. And let's keep the code here, but I just need to use the file size. So once I know the file size, I know, like in this case, if I say these are characters, I know that I need a string of size 8 plus the null byte to store the content of the file. So now we could use, for instance, dynamic memory to create the buffer that we can store the string in. So create the buffer. Today I use Kellogg maybe. So how many elements do I want to use? I take the file size plus an additional 1 for the null byte, and every element is size of character. What do I need to do now? I need to do the null check. If the Kellogg call failed, I want to print something like out of memory. Then I need to return.
Yeah.
Have I forgotten something?
Any ideas what is missing here? Yeah, F close. Yeah. So similar to free, we have to close the file in every possibility where the program will end. So in this case, we have to close it also because it does not come to this line 26. It returns earlier. So yeah, it's pretty similar to malloc and free when you fopen and fclose.
So now everything is properly closed and we can terminate the program basically. And maybe I should also add this here. In the end, I want to free the buffer as well, that we don't forget this in the end. Okay, and now I want to read from the file, and now I can use something that you all know. We can just use fgetS because we want to read a string from a file. And where do I want to store it? In the buffer. How much do I want to read? I want to read
the whole
file.
Yeah.
So let's specify the file size here. Maybe specify the file size +1 because we said fgetS will always also write the null byte at the end. And if I just specify the file size, I will just read 7 characters and store the null byte as the 8th character. So let's go with 1 more that we also store the null byte. And then I specify not std_in as you are used to, but I specify the file now. And now maybe let's print the string then that we have read in. Oh. So, okay, we have printed the string, we have read it with fgetS, but it doesn't print hi ISP. This is difficult. Why has somebody an idea why this is the case? I must admit, when I did the program yesterday, I also had this problem, and this was not on purpose. I had to look at it a bit, and then I found out. But it's really not easy to see.
So the code is generally correct, I would say.
Yeah.
But it doesn't work.
Mm-hmm. Yeah, the cursor is not set back. So we said here, we started with the first position, then set the cursor on purpose to the end, and then we took the file size, but then the cursor basically stayed in this line. If I want to read from here, there is nothing more contained in the file. So if I do this thing with the getting the file size, I probably should also, I could call either rewind to set it back, or alternatively, I could also write fseek, again with 0 offset to seek set. So this is the initial position. So now I seeked through the file, went to the last position, set the cursor there, set the cursor now to the beginning, and now I can read. And now hopefully it works out. Okay, now we have the string hi ISP, and we had the new line here because also there the new line was contained in the file. Maybe you don't calculate the file size in the beginning, so maybe you would like to find out whether you have reached end of file. So we have seen that fget returns null if there are no more characters to read. So if we would call fgetS one more time, then fgetS would return null in this case. But there is also another function, I think someone mentioned before, with feof to check whether there is something more in the file. So maybe print this here. So we call the function feof on the file, and this will basically return have we reached end of file or not. So reached end of file. What does it return? An integer?
Integer, yeah.
Okay, so we print this here, and afterwards, if we run it now, I have not written a \n here, sorry. One more time. So in this case, we have reached EOF at the beginning of the file. Okay, this is not true, 0, false, because there is something more. If we read with fgetS, now the content, the string, then the end of file is still 0, so we have still not reached it, although we are there, but we really need to attempt to read more that we reach the end of file. So if I would call fgetS one more time.
Or just use file size +1 or +2.
Okay, yeah, in this case. Then
we should reach it, right?
No, because the fgetS will stop reading at the \n.
Yeah.
So yeah. So this is maybe tricky, but if we would call fgetS one further time and then print this reached end of file thing, then we will get a 1 here, because in the second call we would try to read starting from the second row, but there is nothing more contained, not a single character anymore. So for this reason, the end of file will trigger, and we can also see this here. Okay. Maybe we keep this.
So one good takeaway is, if you are kind of lost in your file, just print out where you are currently. because it saves a lot of debugging time. For example, when we forgot to rewind and set it back to the beginning and nothing was read. So just print out where you are currently in the file. Of course, you have to somehow read where the characters are and where is your current position. But it will also give you a good idea. Okay, maybe I have an error, or fgets didn't work as expected, or whatever.
Okay, now you have hopefully digested what I said before. When I said, okay, what is contained in the file? Either these 8 characters that we have read in now, but what if we interpret this as 2 integers, for instance?
So these 8 characters are kind of translated to integer or to values, size of a character between 0 and 125, 255, yeah. So they actually have a value. And if you kind of combine this, always 2 and 2, you will also have, or 4 in this case,
yeah,
4,
so 4.
Then you will get another number, basically.
Because we said an integer consists of 4 bytes, so we combine the first 4 bytes into an integer. Okay, now I will not do this with malloc and dynamically allocate the memory for this. I will just say, okay, there are 2 integers now. So let's make an array of 2 integers. And now I want to read the file content into this array. And now I use the function fread. So where do I want to store it? Into this array. What is the size of a data type? This is now size of integer. And how many? It should be 2. And from where? From the file. So this fread then reads these 2 numbers multiplied. So this would be 4 times 2, 8. So it would read 8 bytes and stores them in the numbers array. And this is then coincides with integers. Okay, now let's see. I want to print these numbers. Numbers at 0 and numbers at 1. Oh, and I will not do the mistake again. I will first rewind in the file and go to the beginning that I can read again through the file.
Will the output we get here be meaningful? So, will it be the value of h, I, the white space, and I
no,
combined?
No, because it's not like a multiplication of it or an addition of it. I mean, it is meaningful, of course, but but it's really like the.
So it's kind of an artificial example we are doing here.
Yeah.
It's we just want to demonstrate you it is possible to interpret whatever is in a file in many ways. You can interpret it as integer. You can interpret it as character. To the file, it doesn't matter. It just has a value inside.
So let's maybe see this. If I read this now, there is this number and this number. Okay, these are some arbitrary large numbers now. But maybe, and also in the assignment 4, it will be the case that really the first bytes, the first 4 bytes will coincide with an integer. And depending on what is written there, this should be then the integer in your program. Maybe I can demonstrate this now a bit better. Maybe it's a bit more confusing now, but I hope it's not the case. I will print the numbers now differently. I will print them as hexadecimal numbers. So instead of D for decimal, write X for hexadecimal. And I will artificially add this 0x because you write this if you want to think about the number as a hexadecimal number. And also do this for the second number and print them again. Okay, let's run this. Okay, now we get this output here.
They look like addresses, but of course in this case they are not real addresses in our memory. They're just numbers stored or represented as hexadecimal.
And now the nice thing about this representation is that like the first 2 digits correspond with a byte, the second 2 correspond with a byte, the third 2 correspond with a byte, and the last 2 correspond with a byte. Now I will open the ASCII table with -h so that I don't only get the decimal representation of ASCII character, but also the hexadecimal representation. This looks then something like this. And I'll probably execute the program one more time to make it a bit more, make it a bit better. Okay, what have we now in the file? The first character of our file is an H, a capital H. If I look at the ASCII table, then I have here the capital H and the hexadecimal value 48. And now we see the 48. Now maybe this is awkward why it's at the end, but accept it for a second. The 48 is here contained in the integer. And then if I look at the second byte, the I, the small I is here, so this would correspond to 69, and 69 is the next byte in the integer. And then if the
white space, it should be 20 in hexadecimal.
Yeah, okay, here's the space symbol, and this is then here.
And then we have 49.
The large I, this is then, sorry, wrong table. 49 in hex is the large I, and this is stored here.
But why is it the other way around?
Yeah, this is one more question. This is basically a convention that you store the bytes of an integer in the inverse direction, so that the least significant byte, so the byte where if I change here, if I increment this byte by 1, then the integer would change by 1. And this is stored at the first position in the integer. This is represented by the H. And then the next byte, so if I would increase this byte by 1, the integer would increase by 256. This is then stored in the next position and so on. So they are kind of stored in the reverse way. It is okay if you accept that this is the convention, and if you deal with networks, I think then it's exactly the other way around. So just accept it that it is this way. And if we stick to this way and then interpret the first four bytes of the file as an integer, then we will get this number that we have printed here now. And now I can also do some weird stuff. Maybe I want to go with fseek in the file to the third byte. So basically I seek set is the beginning of the file, and I increase this by 2. So this means the cursor is here, and then I go 2 steps to the right. So I'm here, and now I can also kind of say from here on, from here on, 1, 2, 3, I want to read these 4 bytes as an integer. So I could create like a variable number, set it to null, and read then into the number. Now I need to specify the address because it's just an integer. Size of integer 1, and from the file. And now I can also maybe print this integer. Number. And if I do so, here I can compile. Then I get these bits, and you see they correspond to these 2 and to these 2, because we've read now in the middle. Why do we do this? You need it for A4, and also if you are not interested in kind of printing an integer to a file, then if you represent it like with the byte representation, you just need 4 bytes for every integer. But if your integer would be this number in decimal, then you need, I don't know, 10 bytes. So you need much more space. And for this reason, this is more efficient if you're not interested in really visualizing what is contained, but just say, the bytes are enough. This contains all the information that I need. it must not be like human readable for us.
Is there a way to also look at the file content but in hexadecimal representation?
That's a good point. If you type hextam, and I think -C is also a good option. If you write this command, it's also on the slides then you also see the file content represented by hexadecimal values. So here on the right-hand side, it's the content of the file.
So the interpretation in ASCII.
In ASCII.
Yeah.
And here on this side, you have the bytes. So again, the H corresponds to the 48. In hexadecimal, the I corresponds to the 69 and so on. So this helps you maybe visualizing such a file. And I said in A4, you get such a file and then it will be stated, okay, the first one must be a B, the second one must be an M, and the next 4 bytes are interpreted as an integer, and then the next 4 bytes are interpreted also as an integer, and so on and so forth.
And this is basically where all kind of, for example, images use or store their information. Yeah, so of course the image is not ASCII values, it's just hexadecimal or hexadecimal values, for example. You can also view any image, a JPEG, whatever, using this hexstamp. And yeah, you can see what the values are there inside. Most of them have some magic values in the beginning indicating the data type. But it's very fun and interesting how they're actually stored or what data is stored in a file, for example, in an image.
I could also open maybe the code file now, the compiled code of read file. Let's open it anyways.
Yeah, it's basically not really readable.
But like every element here corresponds to 1 byte. Some of them, as you said, are not readable. Some of them are. So here you can see that some of my messages are also contained in the code. But they are, of course...
Seems like the hard-coded strings are stored somewhere in the program.
Yeah. And then there's some other parts and something is not readable. But we could read the bytes still of it. Okay. Are there any questions regarding the files in C?
Good question. The question is, can we use it for just some kind of files or any kind of files?
You can really write any kind of file with that. The file ending at the end is not really important actually, because
basically a recommendation.
Yeah, so it doesn't matter what file ending you have. You can just write bytes there, and if you would like to have that the file works in some context, it of course needs to fulfill some requirements. You can write the file, or you can write bytes and then call the file something.pdf, but it will probably not work because you have not stick to the conventions that need to be there in a PDF file.
But every file has its convention, and when you stick to this convention, you can create, as you say, for example, a BSD file, a JPEG file, or whatever. And you can interpret it and open it with, for example, any image creator or whatever. Yeah. Okay, so the question is, why do our program know that it's in the current directory? Okay, so that's depending on the path you hand over with F open here. So if you write it like this, it only searches in the current directory. If you want to switch directory, you always have to mention it here. So for example, if you want to go one directory up, you have to write it like this. So this means going one directory up and look there for this file. If you want to go one directory down, let's say there would be another directory, then you have to write it like this. This means going into the KU directory and look there for the file. So you always have to add there the complete path to the file. Yeah. But I think for the practicals, we only work with local files in the current directory, right?
Maybe in some test cases, something is then used like config / then the files are located in the config folder. But for you as a programmer, it doesn't matter in this case.
Because most of the time, these file names are provided by the user, or when we open the file using the command line arguments. So in most of the time, you will specify here just a variable, and the user enters, for example, the path or by the command line arguments.
Mm-hmm.
Okay, so the question is, if we create a file, but the file name is already kind of occupied from another file, that's unlucky because we overwrite the file then.
But it basically depends on which mode you're using. So if you take the read mode, then you just read this file. But if you use the write mode, then you overwrite the existing file. Mm-hmm. Yes, this is possible, but we don't present it here.
Yeah.
But yes, you can do much more stuff like checking if there exists a directory, if there exists a file, what are the files in a directory. All that stuff is possible, but we will not do this. Okay, I think we will.
Yeah, we need to continue to the second big topic today, which are trees. And I have to say here that we will also discuss trees today in the lecture, and because of kind of time constraints, we will move the practical part before the theoretical part. But let's see how this works, because we will discuss, or we will implement a simple tree now, and then in the lecture you will also see kind of the representation, how this really works in a visualization.
Mm-hmm. Okay, then maybe let's try. Let's start with a binary tree, and we will need some definition first. So an element in the binary tree, we will call this a node, or if you come from a graph theoretical point, vertex, but we will stick with the convention node. So like in an array, there are n elements, or in a binary tree we have, I don't know, some nodes contained. And every node is then able to store some data in it. So if we would like to represent an array of integers using a tree, then every node in this tree should contain an integer. But of course, it could be like a struct or some more complex thing as well. And then every node has up to 2 child nodes. So every node has 2 children, basically, or up to 2 children. And every node has exactly 1 parent node. And this is true for all the nodes except for the root of the tree. Okay, now maybe let's draw something. I hope that this works. If I do it like this now. Okay, yeah, you can see this, and you can also see it then in the recording. Now, what could be a tree? So we have a node, and I will make this maybe a bit bigger. The circle here. So this is then a node. And let's write some data in it that is more meaningful. Maybe write an integer, maybe write, I don't know, 5 in it. And this node has then, as we said, 2 children, or up to 2 children. So I will make 2 arrows here.
So what is a children?
This is again a node.
Yeah, it's a pointer to another node.
Mm-hmm. So that's why we have the arrows here. And this is again a node. Maybe we have written here 3, and in this node, maybe 7. And then the node 3 also has again 2 children. And maybe make 1 child here, maybe write 1 into it. And maybe 3 has just a single child. Now to make this in a program accessible, this information, we will still need to store the pointer, but we will write something special in the pointer. We will just write null inside of the pointer that we know, okay, there is nothing more here. And also maybe for the 1, if this is then the last element along this path in the tree, then we also write null here. Maybe the 7 has a 9 and null, and then maybe here we have 2 times null. So basically, if now maybe I should do this. This is actually the 5 is the root node because it does not have a parent. So we make this like this. Okay, so now this is the first node basically in the tree, because there is no node here. So that's why we call it the root, also the Wurzel vom Baum, the start of the tree. And then if we go along the arrows in a path, we visit several nodes, and at the very end, we will then always reach null that we know we cannot go further in this way. So this would be now a tree, and this actually has a nice property, this tree, because if I'm now at the 5, if I go to the left side, all the numbers here are smaller than 5, and if I go to the right side, all the numbers are larger than the 5. And if I maybe pick the 3 here, all the numbers to the right are larger. Okay, there are none, so this is very easy to fulfill, and all the numbers on the left-hand side are smaller.
So this is already a special tree.
This is a special case of a tree. Here, this data could be arbitrary. It's just I drew it this way because I also want to write a program now where everything is sorted in this way, but basically this could be an 8, and this could be a 2, and this could be a 6, and a 3, and again a 2. It doesn't matter. It's just some data structure. But in the example I will show in a few minutes, I really want that this is sorted. And maybe someone remembers this from coding session 2. You did something there. So maybe the idea is already clear. So we can maybe start coding. Okay, maybe switch directly to the code. So I already started here with an array with some values here contained, and I would like now to build a tree up on this. So I will, like the 20 will be the root node, and then I want to insert the 19 into the tree, and since it is smaller than the 20, I would like to insert it on the left side. And then basically continue here. I will probably later draw this also in the picture. Okay, how can we do this? We first need a proper data type to represent this. So we need to define a struct which we call tree node.
So that represents one node in the tree.
If we switch here, so this would basically correspond to, for instance, the 5. And it should contain the integer and the information, what are the 2 children.
So we need here, of course, the integer value to store the value. And we need 2 pointers to the left child and to the right child. How do we write that?
Now this is difficult because the tree node itself is only defined after the struct. So we need to define this with this definition, and we want to have a pointer here. If we would not use the pointer, then the tree node to exist would need a tree node in it, but this would need a tree node in it, and so on. So this wouldn't work. And
same as we had in the linked list last time. So that would not work. So we only need pointers here. So we have a pointer to the left child and a pointer to the right child, which again has a value, and again a pointer to the left and the right child. And if there are no children, or if there is no child, for example, on the left side, then it points to null. So we haven't created the nodes now. So we just have now created the data type, but I think now we should create our root node, for example.
But I will do this, I will not do this like manually, but I really would like to write now a function where like the values are inserted into the tree. So I will start by defining the basic, I need to have some start. I would like to have this pointer, but at the very beginning it should not point to a tree because there does not exist one. So we'll start with a pointer that points basically to null. So I will start with a tree node pointer. This will be the tree, but in the moment it's not there because we haven't done anything. And now I want to write a function that creates the tree for me. So I don't know, create tree. And this returns then the tree. And what do I want to pass? Probably the values.
The values, yeah, because each node should be one value inside.
Okay, so this function that I want to write is a tree node, create tree, and it receives an array. Okay, I passed an array, so we'll probably need the size of the array as well. So this would be size of values divided by size of integer. Okay, so now we create the tree and we have this function here. And now, okay, I start probably also here with the tree, but because we don't have it at the beginning.
Yeah, so in the base case is that there is no root, there is no tree. So in the first case, we have to create the tree.
So I can start with this here. Okay, and now this is even too complex, the task. So I will just do it like this. I will iterate over the array, 0, then like the position less than the size. And then I want to write a function insert sorted. I pass the tree, I pass the value that I want to insert. I get out a tree, and that's it basically. So
now you are iterating over the array, and for each integer in the array, you call this insert sorted. So still, we don't create a tree, we just call this function, which should do what?
It should take the tree that we currently have and put the node in the correct position on the tree.
In the tree. So, okay, in the first case, when it's 20,
it will then basically puts it in the first position here. Yeah. So if we take it in the visualization, maybe write 20 here. I will just have this part of the tree. And everything below here is not there. And when I then insert the next value, maybe I think this was 19 in the example, I will then take the existing tree, and 19 is smaller than 20, so I'll go to the left side and write here the 19. That is the plan. And this should this function do. And so we will always build up the tree, and just let me finish it, otherwise I will forget about it. So if this is done, then I will return the tree. Okay, now
it's getting tricky.
Now the interesting stuff starts. So the tree node, insert sorted, it takes the current tree,
yeah, and one
and the value.
Integer, the value. So in the first case it's 20, then it's 19 and so on. Yeah. Maybe you can close this one below here.
Yeah, maybe make it a bit smaller. Okay. What do we need to do in any case? So if we have this, maybe this is the current tree, it doesn't matter. We first need to create basically a new node. We need to create this. We need to store the value, I don't know, 19. We always need to do this. Independently if there is a tree already existing, or if we want to fill it in some position in the tree, we always need to create this node because there will be a new node created. So we can really start with this operation. We just create the node. We don't do anything with the tree. We just create a node. So we take the tree node and call this maybe new node. And okay, I need to do this now on the heap. So I will call malloc with size of the tree node. If I do this on the stack, then after calling this function, my tree node is gone. So I need to do this on the heap.
Okay, we need a null check, of course.
So if the new node equals null, then I will I'm not sure how I should do that.
I would say return null.
Let's return null, okay?
Yeah.
Now, okay, maybe make it like this. Okay, so this doesn't work. We return null, but if we do it like this, then we store everything. We store in the tree null, so we lose our tree. Yeah, so this is kind of the same thing as with realloc, where if you use the buffer that you pass to realloc, you get it then back, you overwrite it, and you lost your tree. So if I want to avoid this, I should probably do something like tree node, temporary tree. Is this insert sorted?
So if at some point I lose, I cannot get any memory back, I kind of have duplication, or not a duplication, but that's not still the reference to the existing tree. And then, because all the trees elements are on the heap, I have to free it.
So this tree is never touched by this function at the moment, because we just use this malloc call and we don't change the tree, we just store the result in the temp tree. And now we can check if the temp tree is null. What do we need to do then? We need to free all the memory. And I will just write, maybe as a comment at the moment, because we can't do it right now. We want to free the original tree. We never changed it. The insert sorted will never change this tree. So we will free the whole tree, and then we can return null. And we are not done yet. So this is also important. Now the create tree function can also return null, but if we do it like this, we have freed all the memory. So we can really return null here and check here if the create tree returned null, if the tree returned null, and we can terminate the program. We can maybe write the message out of memory. But since we freed everything of the tree here, we don't need to think about freeing anything in the main function, because either there is some valid tree returned or null is returned and everything was freed before. So this is kind of in structuring your program important, that you don't need to deal with that here, but really either get the correct tree or you get the tree that is where you get null and you know everything is freed, everything is already done. Okay, so we have implemented this now, and if it works, I can set the tree to the temp tree. So, and I think this function is now done, because if there is a mistake, or if there's some error happening, then I free everything in return. Otherwise, I continue with the tree and repeat this, and at the end, I return either the tree or null, and I freed everything. Okay, I think this function is already done. So now the insert sorted. Now we have malloc called. We check this. Now we want to insert everything into the node.
So again, this function should first create the node and insert the node in the current tree.
Yeah, exactly.
Where in the current tree?
In the order. I will show this maybe, but first initialize the node if we already have it. So we will store inside of the value the integer, because this is the data that we want to store. And then we will directly set the left child to null, and I will set the right child also to null.
Oh, that's important, because otherwise we don't know what's stored there, and it might be a number that could be interpreted as an address, and we reference to some address which we don't want to refer to. So always set all your children to null. That sounds awkward.
But it's really important that everything is properly defined and not undefined. Okay, and now we basically have to think about two cases. So the case one is tree is empty.
So that's the base case. We basically have the root node, so the first element, then there is no tree, so we have to kind of create the tree.
And we will start with that. Yeah. How can we find out that there is no tree? if the tree is null. Okay, so we can check if the tree is null. What is then the tree? So if we go back to the visualization, now let's stick with the red part here maybe. Maybe make it even a bit larger.
We just created one node.
We have the tree, which is null, and we have the node that we created, and this node, this is a pointer to such a node. This is null, and here we have 20. And now how can we do this? We basically say, okay, the tree should not point to null anymore, but the tree should point to 20. And then this is the whole tree, because we just look at this part. This is a tree. Okay, now we can do this. And we can do this basically, we don't need to do anything in this function. We just return the new node. Because then the new node, if we go back here, is the temp tree, and then the temp tree will become the tree. So this is everything that we need to do, and the base case is done. Okay, yeah? We can do this, but we don't need to do this. I mean, you are right, we should probably do this to fulfill our malloc guide 100%, but we can do this, of course, yeah. So this is the whole base case. So we have done this already.
That's the easy one. Okay, yeah.
And now maybe demonstrate this. What is the next number? It is 19. Okay, if I want to insert 19, what do I want to do?
Should be 19 on the left side, on the right side.
Yeah, so we compare it with the 20. 19 is smaller, so we want to go to the left side and put it here. So maybe check this. Now this is now a bit more involved than just the example.
So in the base case, we have to check if our new node, so the 19, is smaller or equal or higher than the root node in the base case. Yeah? So we have to somehow compare that.
So we basically need to, I maybe write this like this. I want to compare whether the tree, the value of the, maybe make it like, value of the tree is larger than the value that we want to insert, and this means go left, and in the other case I want to go right. So if they're equal, I also go to the right, maybe.
So the tree here is the root node. Yeah.
But I cannot do this just for the tree, because maybe the tree is larger and there is some longer path. So maybe switch to the example back. If I insert, I don't know, let's put this back to 5, that it is ordered. If I want to insert now 2, then I check this node, I need to go left. This node, go to the left, go here. And then here I see 1, okay, I need to go to the right. So I need to implement this going through the tree procedure. So I cannot just do this with a tree, but I need some temporary variable here.
So we have to iterate over the nodes down the tree if we have multiple nodes in our tree. So similar to a linked list, we have to remember what's the root, so what's on top. That's our start. And we need a temporary variable, which we call current node, which always get refreshed to the current node we are iterating down the tree.
For this reason, we also now need to check where we need to go at the current node. So if we go, if the value is larger, so the new value is smaller, we want to go to the left side, we can basically do current node equals current node left. And if we want to go right, we take the current node and go from the current node to the right side. But we just do this now once. How often do we need to do this?
Is twice enough?
No, it is only enough if we kind of went through the tree and reached the null.
So we don't know, we want to program it in a generic way. So we don't know how many nodes are in there and how deep is the tree already. So we need kind of a condition in the loop that loops until we have found our place for our node.
Mm-hmm. And this is given by the null value.
Yeah.
So I do now a loop while the current node is not null. I do this procedure.
Yeah.
Okay, and now at the end, here we know current node is null. Is this now meaningful? Now we have one problem here.
This will end up in an infinite loop.
No, actually it doesn't. It shouldn't be a problem.
Yeah, no, sorry, yeah.
But we have one problem because we said, do we want to insert it here? Yes, no, we want to go to the left side. Do we want to insert it here? Okay. Do we want to insert it here? And then I go down here. Oh, I have now the null, but I cannot insert it at null. I would like to insert it here because at this node, when I was at the one, I saw there is the null. I can insert it there, but this current node has null at the end.
So I should not stop when I'm reaching null, but one step before reaching null.
Yeah. So this is now, I could check also this, but I will use now another idea. I will also create a second pointer with that I iterate, and I will call this the previous node. I will set this to 0 at the beginning. Okay. And now, whenever I start the loop, I will say, okay, the previous node is the current node. Then afterwards, I go left or right and update the current node.
But still have the previous node stored.
Yeah. Exactly.
So I have this kind of link back to my parent.
Maybe in the visualization, this would mean that I have start with the green and the violet arrow. Maybe this points to null at the beginning. So the green is the current node, the violet one is the previous one. Then I will set the violet one here and move the green one to the next element. And then I will say, okay, whoops, this is okay. We can move here and then we move here. Then we say, okay, we're still not the end. We move this here. Then the green arrow moves to the null. And then we still have the violet arrow pointing to the element where we want to insert. That's why we need these two arrows. We also need this for linked lists, if you maybe see this example in the lecture later on. So we really need this. So now, here we know that the previous node points to node where to insert. And now we can do this very easily because we can just check, is the previous node, again, the value, is it larger than the value? Then we can take the previous node and the left child is then the new node, or in the other case, the previous node, right child is the new node. Okay, so this would basically mean in the visualization from before, if we insert the 2, we would be here, and the 2 is larger than the 1, so we take the right child and assign it to the new node where we have the 2, and this points to null. And then we have updated the tree accordingly. So one last thing at the very end, if we do so, we never change, like in this case, in the case 2, the tree is not empty, we never change the first node in the tree, and for this reason, the tree never changes, and we really can return the same tree as before. Okay, and this is now the insert function. So we have the first case when the tree is empty, and then the second case where we iterate through the tree, find the correct path, find the node in this previous node where we want to insert, and then dependingly where we want to insert it, we do it on the left or the right side. Okay.
So this implementation works now, but of course we wanted to print it somewhere, somehow. Do you want to continue, or should we move that to the next week?
When we could continue, it's not that a large thing anymore. So we want to print the tree now. So maybe print tree. Also haven't read it yet, but okay, now don't need to return anything. I want to print the tree. I pass in the pointer to the root of the tree. And now
how can we iterate over this until we reach the left and the right side, and each of it reach null? That's complicated.
So basically, if I would to do this now, I start at the root and then go to the left side, maybe go to the left side, go here to the left side, see there is nothing more. So maybe I print this one, then I go here, print the 2, go back upwards, downwards, upwards, upwards. But what you see here is I always need to go downwards, then I can do stuff in this part, and then I go upwards again. But the problem is, how can I go upwards? Because I have here at this node, I know there's the left side, there's the right side, but if I'm at this node, I don't know how I can go back. So I could implement something now that I maybe insert also these links here that I can go upwards. This is an option. There are also other possibilities, but one possibility is very easy and it looks even magical that it works. You do the following. If I want to print the whole tree, then I print the left tree, then I print myself, and then I print the right tree. And that's everything. Okay, now there's no implementation basically, but that's the whole idea that you need. You print the left tree, then you print yourself, and then you print the right tree.
But I have to do it once again for the left and right tree.
Okay, so if I look at this part here, what is this? This is also a tree. So I can do the same thing as before. I print the left part, this is this, then I print the tree, and then print the right part.
This is actually a good transition to our lecture where we also discussed that. So I think we can stop here and move that to next week, the implementation, if that's fine for you.
But it would be 3 lines of code.
Yeah, but then we have a good kind of,
okay.
They can think of it 1 week, and next week we show them the solution for that.
Then we continue from here next time. I just want to mention one last thing. We will also next time look, as you see, at the tree with arbitrary many children. So here we had the case where we only have 0, 1, or 2 children. Next time we will need to look at the case where we have also more or arbitrary many children, because you need it for assignment 4. So we also need to discuss this a bit, because this gets even a bit more tricky then. Okay, yeah, then we will stop, I think, for today. Thanks a lot. We will start probably with the lecture in, when do you want to start?
Let's say in 10 minutes.
In 10 minutes. Then, yeah, see you next week again. Thank you.
Thank you.